So now Ziggy's talk, he pre-recorded because it's early in Canada, I think. So I'll just play that for us. And a few of his colleagues is online to answer any questions. Jason, does that look okay to you?
Yeah,
Jason?
that looks fine.
Okay, I'll just hit play now.
Hi, I'm Ziggy.
I don't hear Joe because you're muted.
Oh, sorry.
I'd be happy to answer any questions you have in the Slack later after I wake up. But there might also be some members of the Chime FRB collaboration online already at this time. So today I'd like to talk to you about new repeating sources of fast radio burst from Chime FRB, and I'm giving this talk on behalf of the whole Chime FRB collaboration. First, a brief introduction to fast radio burst. And so a typical signal from a fast radio burst is depicted here on the left. So it's frequency versus time in this figure, and you can see the fast radio burst has this characteristic dispersive sweep. This time delay is proportional to 1 over the frequency squared and proportional to the integrated Coulomb density of free electrons along the line of sight towards the fast radio burst. If you integrate over this dispersive sweep, you end up with this d-dispersed time, which you can see over here. You see that the duration of these bursts is about a millisecond. Now, from this dispersive delay, we can figure out that the bursts are very likely extragalactic. And that's because we have a good understanding of the amount of free electrons in the Milky Way. So for this particular source, we know that about this much of the delay is coming from the Milky Way. There's some component from the halo, then a component from the intergalactic medium, and finally some component from the host galaxy of the fast radio burst. So likely extragalactic, but by now we've also been able to localize a handful of fast radio bursts to their host galaxies, and we have been able to measure redshifts from optical spectroscopy for those galaxies. So we truly know that fast radio bursts are an extragalactic phenomenon. At these distances, the output in energy must be large, and we know that the brightness temperatures of these bursts is about 10 to the 36 Kelvin, which means the emission is likely coherent in nature. And we can measure that there's about 1,000 of these fast radio bursts on the sky every day to be detected by modern day telescopes. Interestingly, some FRBs repeat, while some others apparently do not. And some of the sources that repeat periodically. And so that is something interesting. And it begs the question, do all FRBs repeat? And if they all repeat, do they also periodically? And so we have never been able to directly associate one fast radio burst with a cataclysmic event. So it's not proven that they're truly one-off events. And we've also been seeing some differences between repeater bursts and one-off events, most notably in terms of their morphologies. And there's example here from Chime data, where on the left you see typical one-off FRB with broadband emission, narrow in time, and then a typical repeater burst that shows this downward drifting substructure, so burst starting at higher frequencies and then moving towards lower frequencies. So there seems to be a difference. Now, what we'd like to figure out is if they're really distinct populations. So in terms of their repeat rate, there's sort of two possible scenarios. And so it is if there's truly two populations, one-off FRBs and repeaters, looks a bit like this green illustration here, where you have the one-off FRBs with the repeat rate is really one burst ever, and then some distribution of repeaters. And so if you measure all of the repeat rates, or you constrain the repeat rates of all the sources, you will start seeing this difference. Whereas on the other hand, it's also possible that all fast radio bursts are drawn from this broad continuum of repeat rates, where what we currently see as the repeating sources are just the prolific repeaters that are easiest to detect, and the one-off events would be the rare repeaters on the other side. And we can only constrain their repeat rates. And so for now, they look like they're just one-off fast radio bursts. So we'd like to figure this out. And so ways of doing this are study known repeating sources in detail, but also to find new repeating sources. And so searching for repeat bursts, there's sort of two strategies. And first of all, we do know there's many more dim bursts than bright bursts from the same source. And so in general, I guess this is true. And this was very nicely demonstrated for this one particular source, FRB 121102, using FAST, where they measure this really wonderful energy distribution. But in general, the repetition statistics for these sources are largely constrained. So they seem to be non-Pearsonian. Bursts are often clustered, as I mentioned. In some cases, there's a periodic activity in the arrival times too. And so the best we can do is either to revisit or monitor the same patch of sky. And this is something that Chime does, because it just sits there without any moving parts, and the same sky drifts overhead every day. Or you could follow known FRBs up with a more sensitive telescope. And so this has been demonstrated, for example, by detecting repeat bursts with the Green Bank telescope of a source that were originally discovered by the ESCAP telescope, and similarly following up ESCAP FRB with the Murray telescope. And another source has been discovered by following up a FRB originally discovered by the Murray telescope using the FAST telescope. But in this talk, I'll be talking about Chime. So Chime is a Canadian hydrogen intensity mapping experiment. It's located near Penticton in British Columbia in Canada. And so it's at the site of the DREO. You can see there's multiple telescopes there. It's in a natural valley, shielded from radio emissions from nearby communities. And Chime is this is made up of these four dishes here on the left. And so if you zoom in on one of those dishes, this is how Chime looks. It focuses light in the east-west direction onto this focal line, and it basically sees the whole sky in the north-south direction from horizon to horizon. And the focal line of all four half cylinders is populated by 256 dual polarization cloverleaf antennas. So this makes Chime an interferometer, and it gives you the ability to repoint Chime to any part within its primary field of view. And Chime was originally conceived as a cosmology experiment going after 21 centimeter emission from 0.8 to 2.5 redshift. And so this sets the frequency range of the observatory from 400 to 800 megahertz, which is also, as it turns out, a very good frequency range to observe fast radio bursts. And so the Chime FRB project that is looking for the fast radio burst is running in parallel on the telescope with the cosmology experiment, as well as with a pulsar timing experiment. It's making use of the fact that Chime is an interferometer, and within the primary beam of the telescope, we make 1024 digital beams that are static. They just look overhead and they don't track any source. And this gives us a field of view of about 200 square degrees. And as Chime is roughly as sensitive as the Green Bank telescope, this is basically as if we're doing 1024 surveys with the Green Bank telescope in parallel. So we try to do this 24/7 and 365 days a year. And in all of those 1024 beams, we just look for dispersed transients such as fast radio bursts. And then if the algorithms find something, we save the data to disk. And so in terms of repeating sources of fast radio bursts, we've very quickly after returning the experiment, we uncovered that repeating sources are actually the population, it's not an anomaly. So we found second repeating sources of fast radio bursts, colloquially known as R2. And then we found 17 more, so 18 in total at the time they were published. And so there's really a population of repeaters here. Those first 18 are each get a row, and all the colored circles are bursts from these sources. So you can see some of the sources are very prolific, like R2 and R3. We see them very frequently. Some other sources we only see bursts very occasionally. So there seems to be a wide range of burst rates. And by now we're publishing new bursts from these published sources on this website. So you can go to the webpage and be notified when there's new bursts. Another recent highlight is the source FRB 2020-1124A, which you might have heard a lot about. And Adam Lemon, postdoc at McGill, has uploaded a lightning talk on this source. We discovered it very recently, only in November 24 of last year, whereas as you can see in this figure, we did have exposure and also sensitivity to the sky location for multiple years already. And so it suddenly turned on, and a few months later, it actually became, early this year, it actually became very active. And so lots of people in the community, some of you probably out there, have followed us up. Thanks for that. It really showed this what the source really is, and so that's really exciting. So go check out Adam's talk. And for more recent highlights in terms of local universe, fast data versus Chime seeing, go listen to Molly Bartlett's talk in session 2. And so this is just a slide with some lessons learned from Chime FRB repeaters. I'll just leave it up so you can peruse it offline, but I won't have time to describe this in detail. What I'd like to talk about today is our current work doing a systematic and complete search of all repeating sources that are in our database. And so the first step of this is doing a clustering analysis. And so what we do is we look for clusters in sky position and DM from the real-time detection metadata of all the triggers we get in our search. And we take into account the known systematic and statistical insertions in Chime FRB. So these can be from the design of the telescope and also from the design of our search in software. And so that gives us this tolerance that I put here on the slide on the bottom left. So about 13 DM units, about a degree in declination, and about half a degree in right ascension, but corrected for the declination. And so this figure here on the top left just illustrates this for some galactic sources. We find these clusters that end up having the same color. And with this method, we've been able to rediscover all the published Chime FRB sources, so that gives confidence. And it then results in this list of all the candidate clusters that we have to figure out if they're real sources and if they're new sources. And so the next step, having these clusters in hand, is to try to get the best possible sky localization of all the events. And so we use two methods for this. One is to fit per beam detection signals and noises with a B model. And this is also the method we've been using in our first catalog. So this gives about a 15 arc-minute resolution for precision for most events. And another thing we can do if we save the baseband data, so all of the complex voltages at all the antennas at the telescope, we can also brute force repoint the telescope and find the best possible position this way. And this gives about a sub-arc-minute resolution, so much better. And then maybe the most difficult part of the analysis is the chance coincidence probability calculation. So this we have to do because the probability of detecting two unrelated fast radio bursts at high declination with similar DM is non-negligible. And this is because the north celestial pole is always in our field of view. And so we just have a lot of chance coincidences there. And so what we do is we take all of the clusters, all of the events in the clusters, we get the best possible estimate of their sky positions and DM. Then we model all FRB detections as a set of independent Bernoulli trials. And so you get this the sigma DM, sigma RA, sigma DEC little position in the full phase space of the survey. And then we compare these detections with all of the candidate repeater sources. We compare all of the candidate repeater sources with all the FRB detections in the survey. And so this is formalized through this formula here. And so we end up with one number, one probability for each cluster. And then we can set a threshold and we say everything with a chance coincidence lower than the threshold, we deem a real repeater, and we include in our presentation of new sources. And so one interesting way I like to look at this is in terms of our exposure sensitivity as a function of declination. And so I mentioned that we always have the north celestial pole on the field of view. Chime is located at 49 degrees latitude, so we're most sensitive at 49 declination. And this means we have some sort of we have a sweet spot for detecting repeating sources where we sort of maximize both exposure and sensitivity around declination of 70. And so here you see exposure in blue, this gray dashed line of declination above the gray dashed line you see twice a day, one side of the pole and then on the other side of the pole again. And so our first repeater detections really mostly happened around that sweet spot, around declination of 70. These are 1+8 repeaters that we published first. 9 more than, we started filling in some of the more lower declinations. And now with our new sample of at least 15 new repeating sources, that brings us to about 35 repeaters at least in total. And so it's 15 new ones that we, plus the 2 that have been published separately because they were especially interesting. One, the repeater towards M81, and one that's 2020-11-24A. And so you really see that the sample now, we're finding more and more sources at lower declinations and filling in some of the gaps here. And so just some highlights in these new sources. We're finding more sources with downward drifting subburst, as here on the top left. You can see the characteristic morphology in the dynamic spectra. We see a source with relatively broadband emission and also narrow in time. So it's a bit against the dichotomy that we've been seeing between repeater burst and one-off events. But it might just show that also repeater bursts are drawn from more of a continuum of morphologies. And we've also seen similar morphology in the repeat burst from the repeater towards M81. Now we've also seen the source with on the order of 10 detections at the declination of 8 degrees. So we're really finding more of an active sources towards lower declination that might be interesting to follow up from one of the southern hemisphere telescopes. And finally, we see the source at a DM of 1730 DM units, and here are the 2 waterfalls. And so really we start to see more, as our total exposure increases, we see more dimmer sources and that are likely farther out. And so one final thing we're interested in looking at is our detection rate over time. We'd like to see, do we run out of repeating sources, or do we keep on detecting them steadily? So here I'm just showing a cumulative distribution of the number of repeater sources versus time. And now it's very important to note that this is not proportional yet to exposure. And so we have to convert time here into exposure and include sensitivity calculations for this period. So don't read too much into this figure. And also for this new period here on the right, there's additional candidate repeaters that are subject to internal scrutiny. So as we converge on the chance coincidence probability calculation, it is possible that we find even more than those 15 new repeating sources past radio burst. And so to conclude, work is underway to vet all the candidate sources that we found in the systematic and complete search of our database. This will roughly double the number of known repeating sources. We're investigating our detections versus time and see if we can get some signs out of that. And then also just to note that active source can still suddenly turn up, like FRB 2020, 11, 24A. So we should definitely keep looking. Thanks.
All right. Well, thank you, Ziggy. Hopefully you'll see the applause later. That was very interesting talk on repeaters. Have we got any quick questions? Because we do have some of these colleagues online. Obviously, you can always put these questions also in the Slack. Yeah, Jason, would you like to ask?
Yeah, I guess the question I had, so there was a recent paper by Brian Metzger talking about a toy model in which kind of the duration of FRBs would be inversely proportional to their bandwidth and frequency. That you know, if you see broadband emission, typically the burst will be narrower in time. So I mean, there is this apparent dichotomy between repeaters and non-repeaters in terms of their widths and bandwidths. But if you look at just the repeaters themselves, do you see this kind of trend, evidence for this trend?
I think Ziggy nominated Pragya. I don't know if Pragya wants to field that question.
So basically we currently are mostly working on getting the localizations for these repeater candidates and have not characterized all of their properties. So that's not a question that we can answer right now, but I believe that once we do like the property characterization, we do have a large sample to test this theory against.
Okay, thanks. Yeah, that would be interesting because the first repeater 121102 seems to show this actually, this anti-correlation. Yeah.
Mm-hmm.
Cool. Well, let's continue the conversation in Slack/GatherTown. Can I ask Calvin to share his screen? Who's the next speaker? Calvin will be talking about one-off FRB localized with VLBI and Chime. Do you just want to share your talk, Calvin?
Yeah, absolutely. Thank you, Joe. Give me a moment to share my screen. Right, can you see these slides? Oh no, I've revealed the
Secrets.
Yeah.
Spoilers.
Let me fix this.
That's
Give me a
okay.
moment. All right, can you see this?
Yes, we can. You can see the address bar, but I assume you can navigate that fine. Okay,
Yeah.
I'll let you take it on away, Calvin.
All right, thank you for the introduction, Joe. As Joe said, my name is Calvin, and I'm a graduate student at MIT, and I'm also here on behalf of Chime FRB, presenting the first localization of a non-repeating FRB to its host galaxy using VLBI. I'm lucky and proud to be the messenger today, but I want to emphasize that this localization is a culmination of the hard work of a big group of great people. And along the way, I want to highlight some of the technical developments that have led to this accomplishment. So in particular, I want to highlight the lightning talk of my colleague Pranav Sanghavi, who led the instrumentation for one of the outriggers that we used for this localization. And he has a lightning talk here at SALF. So please check that out if you're interested in VLBI localizations. For those of you who haven't heard, Chime is the Canadian Hydrogen Intensity Mapping Experiment. It is a phased array beamforming interferometer working at sub-gigahertz frequencies, mapping a big strip of sky overhead, as you can see from this picture here. This makes it an excellent FRB discovery machine, but our baselines are so small that we don't have the capability to localize with sufficient precision the vast majority of FRBs that we detect to the host galaxies. Our native resolution using Chime alone is just about an arc minute. And today we are in the process of changing that. I'll talk about the first homegrown Chime FRB localization of an FRB to its host galaxy with 50 milliarcsecond precision. How do we do that? We use VLBI with passive outrigger telescopes pointing at the same field of view as Chime. The idea is that these outriggers will just be passive and they'll buffer data, and Chime will do the heavy lifting and detect lots of FRBs and send triggers over the internet to the two outrigger stations, and you can see here. On the left, you have Chime, and on the right, I've shown the two outrigger testbeds that we've used for this localization. And those are a 10-meter telescope at Algonquin Radio Observatory, or ARO, and the 8-dish tone array at Green Bank. Here's a more precise map of our baselines. Unlike traditional VLBI, we're not interested in imaging because FRBs are point sources, and this makes our job a little bit easier since we only care about astrometry. Our baselines are on the order of 3,000 kilometers, and we expect this to give us about 50 milliarcsecond precision. And I'm happy to say that we've actually met that expectation with our results today. One of our outrigger testbeds is an old dish at ARO, which we've parked at a declination of 21. It's outfitted with baseband recorders that allow it to dump crab giant pulses during the transit of the crab through our beam. And so we use one crab pulse per day, a giant pulse that's triggered by Chime as a phase calibrator. And at ARO, there's an active hydrogen laser to keep precise timing between crab transit spaced by 24 hours. Our ARO lead is Tomas, who is a grad student at the U of T. And he's going to be in the job market this year. So we just put out this instrument paper demonstrating the detection of this FRB and the cross correlation on the ARO baseline. Our second outrigger is an interferometer with 8 dishes at Green Bank, built and commissioned by Pranav Sanghavi and Kevin Bandura. It's also pointing at the same declination, and the interferometer has 30-meter baselines. So to use tone in VLBI, we phase up those individual dishes with beamforming, and then use those same set of crab giant pulses for phase calibration between Chime and tone. To see how this works, Pranav has a lightning talk, which I would encourage you to all check out. This year, over the summer, we were observing crab pulses as usual to characterize our clocking systems. And then this monstrous FRB happened at a declination of 21. It was super bright and has a DM of about 500, indicating its extragalactic nature. And we happen to be recording crab pulses shortly before and shortly after the event. So you can see the detection in these waterfall plots on the left and the right. You can see the detection of crab giant pulses at each station individually. And we correlate those crab pulses to do phase calibration and correct for clock offsets. Unfortunately, the FRB is not detected in autocorrelation for at the outrigger stations, which are much smaller than Chime. However, we're still able to detect the FRB in cross correlation of the voltages between Chime and the two outrigger stations. The combination of these two crab pulses before and after the FRB are crucial because they allow us to bookend the FRB on both sides, and that makes sure there's no timing extrapolation necessary for our localization. In parallel, we have independently demonstrated that our clocks are stable on 2-week-long timescales at the 100 picosecond level. Here I reproduce a figure that's in a paper by my colleague Juan Manapara, myself, and our undergrad Savannah Carey at Wellesley. And in the top plot, I've shown measurements of our clock jitter using two different methods. First, from interferometric observations of Sig-A, and second, from direct comparison to a maser. And you can see that the two methods agree, showing that we have control of our clocks at the 100 picosecond level or better for about 2 weeks at a time. And this is how we compensate for clock jitter, and that's the procedure that we take to interpolate for the clock delay between the crowd pulses at the epoch of the FRB. I hope I've convinced you that we have all the ingredients for a nice FRB localization. The next thing we need to do is to perform the localization is a delay model. We use the standalone delay model, DefectsCalc, to calculate the delay in the time of arrival at an outrigger station. This turns out to be on the order of several milliseconds. If you detect an FRB at Chime, like shown here, the sweep arrives about a millisecond later at a putative outrigger station, as I've indicated with these arrows. And the idea is that if we measure the delay, we can translate that into an angle in the sky. While this picture is helpful to build some intuition, it's actually not exactly what we do and inadequate in the way that I'll now describe. The reason it doesn't work is the Earth is moving. During the dispersive sweep, the Earth will rotate by enough that you get a different delay at the start and the end of the sweep. A pulsar like the crab has a dispersive delay of about a second in our band, but for a DM500 FRB, like the one that we just got, the sweep lasts for 10 seconds, and that means this effect is magnified by a factor of 10 for FRBs. So at the start of the FRB, we'll have some delay value, and 10 seconds later, that delay will have shifted. And this rotation is really only significant for FRBs, which have sufficient dispersion measures to make this important. So what have I done here? I've taken the purely geometric effect of Earth rotation and a dispersive delay, and it looks like I've been able to introduce some average delay and a change in delay across the band. And so that delay has a frequency independent piece shown in black and a frequency dependent piece that comes from this changing delay effect or a delay rate. Empirically, it looks like we've just changed the TOA and added some delta DM. And if you work through the math, it turns out that it looks exactly like that in the phases. In addition to this purely geometric effect, there are actual frequency-dependent delays because the ionosphere has different thicknesses at the two stations, and this adds another frequency-dependent piece that is perfectly degenerate with the other one. If we look at the phase of visibilities, we are going to hope that these three contributions give us two distinguishable pieces, one of which has a linear frequency dependence and one of which has an inverse frequency dependence that goes as 1 over nu. And we can use our wide fractional bandwidth to separate the two pieces, simultaneously fitting for a delay and a delta DM on each baseline. This is what that procedure looks like in the space of our data. On the top, I plotted the lag correlation function, and you'd expect a delay to be easily visible as a shift of the peak position. Okay. To resolve the frequency-dependent piece of the delay, we need to look in frequency space, and that's what's shown in the bottom panel. I've taken the Fourier transform at the top, and I plotted the phase as a function of frequency. And remember that we're looking for a component that looks like 1 over nu from the delay rate. It's not super easy to see this, so I'll do the fit for you right here. This is the same thing but with the model overlaid. And we can do this for both baselines simultaneously. You can see that there's some curvature in the model due to the 1/nu piece, as well as a small amount of residual delay that I have not removed yet. This visualization is really meant to highlight the curvature in the phase function frequency. We're not exactly fitting for a delay. We're actually fitting for an RA and a DEC and a combination of 2 delta DMs, 1 per baseline. And here is the results of our full fit. The localization contour that we're looking for is the MCMC corner plot on the top left. And the likelihood islands are a natural feature of our sparse coverage of the UV plane. The lobes are not all equally tall, and if you restrict yourself just to the 3 sigma lobes, you get these shown in sort of an orange-red color. When you overlay that on top of the sky, here is the punchline, which I accidentally showed already. On the right, I've shown our field of view as well as an inset showing our localization with those same 3 sigma lobes. You can see that even with this likelihood, the multimodal likelihood, we've localized the FRB to within a circle of radius 15 milliarcseconds, which is smaller than an optical pixel in the corresponding image from the CFHT. And at that point, I said my job was done. The galaxy has a redshift of about 0.17 and is a few times the size of our Milky Way. The optical analysis is still ongoing, but one thing that we can immediately do is measure the offset of the FRB from the center of its host galaxy. At a redshift of about 0.17, the angular diameter distance implies a projected offset of about 9 kiloparsecs from the galaxy center. I've taken this figure from Shivani Bandari's 2021 paper showing the distribution of host offsets as a function of types of transients. FRB lines are shown in black, blue, and red, and our measurement sits right there in the center of that distribution. This convinces that we're not doing something grossly wrong. However, this is just the start of the game for this localization, because this host galaxy is very, very close to edge on. And this might make you excited because for a perfectly edge-on galaxy, you would be able to use this astrometry to constrain, if not determine, the disk distance. In other words, the distance between the galactic disk and the FRB. And the disk distance has implications for progenitors. So for example, it's known that for magnetars are confined quite tightly to their disks, whereas, for example, a globular cluster origin, like that of the M81 repeater, you would expect to find that globular cluster in the halo. Now, amid all this excitement, I want to give a reminder that this is just the beginning of a long instrumentation campaign happening as we speak. So in this talk, I've demonstrated that we've written our VLBI correlator, kind of understand our systematics and our timing, and we're in the process of building more telescopes so that we can have this level of localization on every FRB that Chime detects, a vast improvement from the current standard of about an arc minute. Let me show you some photos from the outrigger sites as we're building them, and then I'll conclude the talk. We will have, at the end of the day, we're going to have Chime and 3 other cylindrical outriggers located at a combination of long and short baseline lengths. The first outrigger that we're building is in Allenby, BC. That name might change, and it's located at a baseline of about 66 kilometers away from Chime. We'll have another cylinder at Green Bank. It will be tilted such that it can look at the same field of view as Chime. And we'll have a third cylinder in Hat Creek Observatory in California. And with a combination of these 3 outriggers, all passively recording baseband data and receiving triggers from Chime, we'll be able to localize all of these FRBs to their host galaxies and beyond. For our first site in Allenby, we started with the green field earlier this year. And this photo was just taken a few weeks ago. So we have a cylinder up, and this photo was taken by Jane, who is our Allenby lead. We're going to be on the sky in a couple of months from now, hopefully this winter, pending some hardware delays. Similarly, at our second site, this picture was taken in July, and a couple of weeks ago, the foundations are already in the ground, and many of the analog parts have already arrived. Here are Kevin and Pranav, who are our leads for Green Bank. We expect to be on the sky in summer 2022, and we will be getting FRB triggers shortly thereafter. Here's our third site. It's just a greenfield for now, and it's the least far along, and so this is the only picture I have. And we expect the timeline here to be about half a year behind Green Bank.
It's a 2-minute warning, Calvin.
Yeah, that's the end of my talk actually. So it's perfect. So I'd like to thank all my collaborators, the ones I've highlighted, as well as all the other folks who I didn't get a chance to show their picture at a variety of Chime institutions. And I'd like to open the floor for any questions. Thank you.
Yeah, thank you, Calvin. Awesome work there. Amazing localization. Have we got any questions for Calvin online? Yeah, Jason, go ahead.
Sorry, let me just find the, oh yeah, mute button. Hi, Calvin, great talk, very exciting. Can you comment a bit on, so this particular burst was at the same declination as the crab. Can you comment a bit on the calibration challenges for other declinations where you might be more starved in terms of bright pulsars to use to calibrate?
Yeah, so currently we are calibrating using single pulse, using single crab giant pulses. This is something that we can do for the crab, but obviously not for all pulsars. So we are in the process of building a real-time software infrastructure to track pulsars at other declinations as they transit through our beam. So we don't need to rely on the pulsars being giant pulse emitters. But we'll have pulsars at a wide variety of declinations, and then we can do something like trigger on the FRB and then turn on the tracking beams to track pulsars that are close by before and after the FRB arrives at a similar declination. And so the goal is that with a combination of single pulses with our current systems and the upcoming tracking beam system, we'll be able to do phase calibration at a wide variety of declinations.
Okay, thanks.
Any other questions for Calvin online? I had a very brief on Calvin. Now, I'm sorry, I definitely don't know this field very well. I was interested in this FRB you're showing here, the detections. You have like kind of hyperbolic lines running off the side, and I assume the thing on the right is another burst that you just caught as well, and it just happens to be in the same time interval, or just trying to interpret what you're showing here.
Yeah, it's a great catch, Joe. So there are a couple of things going on. There is the main pulse, and on the right, you are right to say that there is a post cursor of this extremely bright FRB.
Yeah.
That's real astrophysics. But the two parabolic lines that are diverging as you go from top to bottom are actually spectral leakage artifacts that are well characterized within Chime. And actually, Ziggy led a lot of this work. So that happens whenever we have a bright FRB, and the contribution of that we call it spectral ghost to our flux and fluids measurements is pretty well understood. So that's an instrumental artifact.
Cool. All right. Thanks. All right, Calvin. Thank you again. That was a lovely talk. As usual, the conversation can continue on Slack and also GatherTown after this. So just ask you to stop sharing now, and we'll now introduce the next speaker, which is Parasar, who will be talking about, it's kind of a good combination, back-ending narrowband giant pulses from the crab pulsar and its potential connection with FRBs. So feel free to take it away, Parasar.
Yeah, can you see my screen?
Yes, we can see your screen.
Great. So yeah, hi, I'm Parasar. I'm an undergraduate student at the University of Toronto doing research at the Canadian Institute for Theoretical Astrophysics, and I'll be looking for graduate schooling next year. So today I'm going to be talking about narrowband giant pulses from the crab pulsar. And this talk is based on a paper that we recently published in MNRIS with my advisor, Shushan Lin. And I want to thank the organizers for allowing me to have a session at this conference. So first, just a brief outline. I'm going to do a little bit of background on the crab, its giant pulses, as well as a bit of background on fast radio bursts. And then I'm going to talk about the observations, so what telescope we used and what data we have. And then I'm going to explain some pre-processing steps, including a new singular value decomposition technique that we used for the dispersion measure correction. And then I'm going to go into the main results, which include the 6 narrowband pulses that we observed, as well as the statistics of all the giant pulses that we observed. And then I'm going to talk about the implications, especially this, we think this research could have for FRBs. And lastly, I'll conclude. So first, on the crab pulsar. So the crab pulsar is a millisecond pulsar. It has a period of about 33 milliseconds. It's located about 2 kiloparsecs away and has a radius of about 10 kilometers. And it's visible from radio to gamma rays. And the most important feature of the Crab pulsar for this talk is that it emits what are known as giant pulses, which are pulses that are very bright with fluences of thousands of Jansky milliseconds at 600 megahertz. And so what you see on the screen in front of you is an example of a broadband giant pulse at a central frequency of 600 megahertz. And it's very bright, as you can see. And so the value of that is that we can study the individual properties of each pulse rather than having to fold them all together to be able to study it. So that allows us to be able to do these spectral studies that we're going to be doing today. So fast radio bursts, you've heard about them today. This is the same plot that I think Ziggy showed, or related plot that Ziggy showed in his talk. But fast radio bursts are bright radio transients with durations of milliseconds, fluences from a few to hundreds of Jansky milliseconds. And they're primarily extragalactic, but we have observed them in the galaxy before as well. And the main feature of FRBs that are important for this talk is that, in general, the non-repeating FRBs typically show broadbanded features, whereas the repeating FRBs typically show narrow-banded features. And so the two panels that you see from in front of you here are from the recent Chime FRB burst catalog. The left panel shows the non-repeating FRBs. The right panel shows the repeating FRBs. And if you look at the left panel, you can generally see that the flux seems to go across the entire band, whereas in the right panel, it's more limited to a subband. And so this is an interesting discrepancy between the two. It could suggest a different kind of emission mechanism between the two. And related to this presentation, we also observed narrow-banded features from the Crab pulsar, so we think they could be related in some way, maybe by the emission mechanism. So now onto the observations. So we observed the Crab pulsar at the Algonquin Radio Observatory, which is a 46-meter dish, and it's located in the province of Ontario, Canada. So we recorded on 25th of April, 2018 for a total of 77 minutes. This was broken down into two scans of 49 and 28 minutes. And the baseband, and we processed the baseband data using a Chime acquisition board. The baseband data itself consists of 1,024 frequency channels between a frequency range of 400 to 800 megahertz. It consists of 2 linear polarizations and 2.56 microseconds of time resolution. So it's pretty high resolution data that we can use for a pretty fine spectral study. So first, now onto the pre-processing. So the first pre-processing step is, of course, the giant pulse de-dispersion. So we have to do this because the interstellar and intergalactic mediums are not empty. There consists of a frequency-dependent index of refraction that leads to certain frequencies arriving sooner than others. And so that's what you see in this panel right here, this black and white panel, where the high frequencies are arriving sooner than low frequencies. And so to correct for this, we need to use coherent de-dispersion. And this is characterized by a number called the dispersion measure, which represents the integrated column density of electrons between us and the line and the pulsar. And the DM that we used is 56.77. And after we correct, we end up with this right panel here. And you can notice that there's a little bit of leftward curvature. So we had to correct for that. That indicates that this dispersion measure is not optimal. And I'll explain the procedure that we used for that in a moment. So after de-dispersing, we used a rolling boxcar giant pulse search to search for pulses with a signal to noise ratio of greater than 5. And the window that we use is about a 0.3 millisecond window. In total, we discovered about 20,000 triggers, and we narrowed them down to about 1,500 giant pulses by looking at signals that had a signal to noise ratio of greater than 9. So now for the DM optimization itself. So to do the DM optimization, as you can see, this is bending. We want to straighten it out, basically. So we use singular value decomposition. And the way that we did this was by, so the left here, PFT, is the dynamic spectrum. And we break it down into one eigenvalue, it's Sn, and 2 eigenfunctions. So UFN here is the eigenfunction in frequency, and V and T is the eigenfunction in time. And we can break it down into the sum of these modes. And so the basic idea here is that the dispersion measure will change the value of this primary eigenvalue. So what we can do is try a whole bunch of different dispersion measures, see how the primary eigenvalue changes as a function of this dispersion measure, and then we can see which primary eigenvalue yields which dispersion measure yields the largest primary eigenvalue, and then that's the DM that we'll actually choose. So the main goal of doing this is that it increases the signal to noise, and therefore that means that there's going to be more pulses that will actually reach the low-level signal to noise threshold that we have. And a higher DM also means that we can have more accurate spectra, and that'll be important for our spectral study. So just a little bit more detail. So the panel that you see on the left is the panel of this primary singular primary eigenvalue against the signal against the dispersion measure. And as you can see, it increases with respect to dispersion measure, reaches a peak and then decreases. And this peak is located at about 56.7563 parsecs per centimeter cubed. And so that's the dispersion measure that we ended up using. We researched the data with this dispersion measure. And so panel B shows the same plot that you've seen twice before now. It has this leftward bend, but that goes away once we correct with this dispersion measure. And so panel D, this shows the eigenvalue as a function of mode number. And the red dots show this for the unoptimized dispersion measure, whereas the black plots show this for the optimized dispersion measure. And really what we get from this is that most of the information is contained in, for the optimized dispersion measure, that is, most of the information is contained within the first mode because the eigenvalue rapidly decreases after that. And the same thing you observe here. This is the eigenfunction in time, and really it represents the time series. And you can see that the black line, which represents the optimized DM, it goes to the noise level faster than the unoptimized DM. And so that indicates that really we've done our job when we corrected for this dispersion measure. So next, the RFI masking. So of course, there's going to be radio frequency interference, and we need to make sure that we don't include that in our analysis. So to do this, we define a region known as the on-pulse region and the region known as the off-pulse region. The on-pulse region contains the pulse, whereas the off-pulse region contains the noise. And the idea is to remove channels in which the noise varies too quickly, which indicates that it's unphysical. And so to do this, we calculate the mean and standard deviation of the noise for each frequency channel. And then we calculate how this mean and standard deviation change as a function of frequencies. We calculate the derivatives. If they change really quickly, so they exceed, for example, 1 standard deviation above their means or below their means, then we mask the channel. So here, the top plot shows the gradient of the noise of the mean. The middle plot shows the standard deviation of the noise, and the bottom plot shows the gradient of the standard deviation of the noise. And these are all functions of frequency. And the upper threshold here represented by the blue line, and the lower threshold here is represented by the green line. And so any channel, any function, anytime it reaches above or below these thresholds, we mask the channel, which is indicated in red. And around 10 to the 20% of channels are masked per pulse. And so after doing this, to get the spectral profile, we need to rebin the data into 64 channels by grouping it into 64 groups of 16 channels each. And then we average over those 16 channels. If the group of 16 channels consists of 7 or more channels that were masked by this procedure, then the rebin channel will also be masked. And so typically we end up with, sometimes we have 64 out of 64 channels, but sometimes we get 63 out of 64 channels as well. So on to the pulse fitting. So traditionally we would fit a power law to the spectrum, but this only really works for broadbanded pulses. But the nonlinear structure of the narrowbanded pulses, like you see on the right here, means that we need to use a little bit more of a complicated fitting technique. And so we opted for this parabolic fitting, where the nonlinear structure is captured by this beta log f over f naught term here. So f naught here, we chose to be the central frequency in log space of about 566 megahertz. And the three parameters to be fit are alpha, beta, and kappa. Alpha here represents the spectral center relative to the central frequency. Beta tells us about the bandwidth, and kappa relates to the amplitude. So now onto the main results. So first, the statistics. So what this panel shows is the distribution of the parameters for all 1,578 pulses that we have. So the blue is the is broadband, while the black is narrowband. And panel A shows the beta versus the alpha, panel B shows kappa versus the alpha, and panel C shows kappa versus beta. And the main result that we get from this is that the beta is the best discriminator between broad and narrow banded behavior. And so if you look at panel A, it clearly distinguishes two different populations. So you have all of these broadband pulses that are huddling up near zero, and all these these 6 narrowband pulses that are outliers of this. And this makes sense because for broadband pulses, we expect beta to be around 0 anyways, because we can fit a power law pretty well with them. And so the narrowbanded structure is really characterized by this beta value. And we also notice that when we hold alpha and beta at their population averages, that a beta value of around -30 is when we begin to notice strong narrowbanded features. So this is another indication that we can use this beta value to predict narrowband behavior. We also find narrowbandedness at different brightnesses, as you can see in this panel, panel C. So kappa is not a really good discriminator between narrow and broadband behavior, and neither is alpha, because we observe narrowband properties at a wide range of central frequencies. So now here are the 6 narrowbanded pulses that we've actually observed. So these are the first 3. The top is a time series, the middle panel is the dynamic spectrum, and the right panel is the time averaged spectrum. And so this table contains all the information we have about these panels, but there are really two main important variables to be considered. The first is the main pulse and interpulse, which stand for the, which is the MP-IP here. And in general, we found that each of these pulses had a phase that lined up with the main or interpulse, which suggests that they are real pulses rather than noise. And we also found that there were an equal number of main and interpulses, which could be interesting to note. And the second important variable is delta nu over nu here. So this is a dimensionless term that we call the fractional bandwidth. Delta nu particularly is the full width at half maximum of the pulse in frequency space. So it represents basically the size of the pulse in frequency. And the nu represents the central frequency. And so we observe this because it basically tells us how big the size of the pulse is relative to its central frequency. And so we also notice that the pulses have different, we also notice that the pulses have different spectral centers, which is why alpha, again, was not a very good discriminator. And in general, narrowbandedness appears not to depend on situational factors like brightness, phase, or the observed frequency band. It appears to be something that's very intrinsic to the source. And so that could be an interesting thing to note for theorists. So one thing that we noticed, at least with panel A, was this potential hypernarrow emission. So if we look closely here, it seems to go out a bit further and it seems to be a bit brighter than normal. And if we look in the right panel, indeed, there seems to be this bright spot here. So we want to look at this a little bit more carefully. So if we look at it and if we look at the spectrum, what we find is that this is a really short-lived phenomenon. So there's this black plot here, this dotted black plot that shows the spectrum at an earlier time. And then we notice that there's this hypernarrow emission around 500 megahertz. And then it lasts for maybe 30 microseconds and then it goes away. So we wanted to know if this was real. First, we ruled out interstellar scintillation since it predicts modulation on the order of around 30 kilohertz, which is a bit too small compared to the 390 kilohertz resolution. And what we needed to do to see if this was physical or not was to compare the microstructure against the noise fluctuations of the on-pulse region. And so to do this, we multiplied the noise by a factor of 15, which we found to be the factor between the signal baseline of the on-pulse region and the signal baseline of the off-pulse region. And then when we compare the hyperemission against this new baseline, we find it doesn't reach a 3 sigma significance. And so we do think it's most likely to be due to statistical fluctuations, which is unfortunate because this could have been very interesting. So now the last thing that I want to talk about is this connection to the narrowband repeater. So a few things here need to be mentioned. So the first thing is that this narrowband repeater, FRB 2019-0711A, it was first discovered as a broadbanded feature by the ASCAP telescope. And then 3 weeks later, it was observed by the Parkes telescope. And in that time, the emission center, two things are of note. First, it was first broadband, and in the second feature, it's clearly not. And the second is that the frequency center shifted. So here, the frequency center is around 1200. Here, the frequency center is around 1350. And if we calculate the delta nu over nu for this narrowband repeater in the right-hand panel, we find is that it's around 0.05. So comparing that to the delta nu over nu that we observed for the crab, which had a range from about 1.1 to 0.25, we think these values are pretty close together, but we do need a bit more data to see if the crab narrowband can reach to lower values like this. We also need a little bit more data to be able to accurately estimate the ratio of narrow to broadbandedness, because currently we have around 6 narrowbanded pulses in a sample of 1,578, which is a very small percentage, but in a larger data sample, we could maybe see if this is more common. Whereas here with the FRB 2019-0711A, we have a basically one-to-one comparison right now. So we need a little bit more data to make sure that this connection is clearer. But overall, what this suggests is that both of these situations, we see narrowbanded behavior at around a similar value range. And so this is interesting to note.
Just a 2-minute warning.
Yeah, thank you very much. Just about to summarize. So what have I shown for you today? So first, the main result that I wanted to share was the 6 narrowbanded giant pulses out of a total of 1,578. These are importantly independent of signal to noise. So brightness, they're independent of phase, and they also need to be independent of spectral center. And so we think that if we had a larger sample potentially a wider range, a wider frequency bandwidth, or we look at lower frequencies, we could maybe find more FRBs because they, sorry, not FRBs, more of these narrowband giant pulses since they appear to be independent of all these factors. We also think there could be a connection with the fast radio burst emission mechanism via this parameter, the delta nu over nu, the fractional bandwidth. I also talked about the singular value decomposition that we used to correct the dispersion measure, which allowed for a very accurate dispersion measure of 4 decimal places that we could use for the study. I also talked about microstructure studies and how we used, we ultimately ruled out this hyper-narrow emission, but we think future studies should look at this a bit further because it could reach the brightnesses observed by fast radio bursts. And lastly, one thing that we would like to do in the future, as well as encourage others to do, is to do more subband searches, because these hyper-narrow emission and this narrow emission might not be observable in the standard broadband searches. And so if we do more subband searches, we would have a much higher likelihood of finding these kinds of pulses and potentially more interesting phenomena to boot. So thank you very much for listening, and I'll take any questions.
Thank you, Parasar. Awesome work. Really good work, particularly for your career stage. Have we got any questions online? Jason, go ahead.
Yeah, sorry, I keep asking all the questions. Very interesting talk, Parasar. Apologies if you mentioned this already, but do you see, for these narrowband giant pulses that you detected, do you see that they have different temporal widths compared to the general, the broader band giant pulses that were detected in your sample, coming back to, what we were discussing a little bit earlier from Ziggy?
So I didn't mention this in the talk. On the top of my head, I don't think that we observed different temporal widths. They appear just by eye to be around the same as what we observe for broadbanded pulses as well. So they don't seem to indicate anything special in that regard.
Okay, thanks.
Yeah, no problem.
Any other questions for Parasar? I had one. If you could go back to about 3 or 4 slides where you were showing your narrowband pulses, I think this one here. Sorry, yeah. So I was just interested in, so you were saying, okay, we're seeing this small structure on top, and then you kind of have this broad underlying structure. And clearly this looks like a signal and noise thing to me, or you were trying to say it wasn't. So like on the left, obviously you got a peak brightness of 2000 Janskis, right? And then this substructure that spins to the right, that drags out. But the one on the left is only 500. I was just thinking about the correlation with FRBs, right? Where this you tend to have narrow pulses without any of this extra structure around it. I know, maybe I didn't fully understand you. Is this a signal noise effect or not?
You mean the hypernarrow? Is it a signal to noise effect?
Yeah, well, I just mean in terms of over the top of this broad kind of profile on the left, so you've got like a narrow structure, don't get me wrong, but then this thing's, it kind of hangs out to the right. While on FRBs, you don't only repeaters do you see such structure, right? Single bursts tend to be much more narrow.
Oh, this extended feature here. Yeah. I'm not exactly sure. I think it would most likely be due to a statistical fluctuation effect as opposed to anything physical.
Okay. Yeah. Yeah. I maybe clarify my question in Gather Town or something. I don't think I got it across. Any other last questions for Parasar? Yeah, Joe Lazio. Go ahead.
Hey, good morning. Interesting result. I'm curious. I was just scanning the paper that you put on Astro PH, and you did not consider plasma lensing to be too likely of an explanation. Can you expand upon that a bit more?
Yeah, so for plasma lensing, the problem with it was more the fact that we would expect there to be a lot of pulses in succession to have similar narrow features if plasma lensing was the cause, because we would expect there to be multiple features within the same time period while the plasma lensing is occurring. But the narrow-banded features that we observed were not, they weren't within a grouping of time. They were sort of sporadically dispersed in the entire observation session. So if it was due to plasma lensing, then it would have to occur on multiple different occasions and only lead to one pulse in each time that it occurred. So that's why we think it's less likely.
Okay, thanks. I might have a couple more questions in Slack.
Okay, sure, thanks.
Sounds good. All right, thank you again, Parasar. Lovely talk. Now, Akshatha, do you want to share your screen? This is our last talk for the session on fast radio bursts with the LOFAR telescope.
I'm sharing my screen.
Yep. All right,
Can you
great.
see my?
Yeah,
Okay,
everything's great. Feel free to take it away.
Yeah. Hi, everyone. I'm Akshatha Gopinath, a PhD student at the University of Amsterdam. Today, I'll be talking about observing fast radio bursts with the LOFAR telescope between 110 and 188 megahertz. As you must have all heard in this session multiple times before, fast radio bursts are very energetic, millisecond duration radio signals from extragalactic distances. Now, as the fast radio burst propagates from its host galaxy to us here in the Milky Way, it undergoes various propagation effects such as scattering, dispersion, etc., which are very frequency dependent. So LOFAR being at lower frequencies, all these effects become more pronounced at LOFAR frequencies. Here I have sort of a typical burst representation from an FRB without any of the propagation effects included. It is also narrow-banded in frequency since most repeaters show narrow-banded emission. Let's look at how dispersion affects this burst. Since dispersion scales with the inverse square of frequency, you have this sort of quadratic sweep in the dynamic spectrum of the FRB. It can also undergo Faraday rotation while passing through an ionized and magnetized intervening medium where the polarization angle of the FRB rotates as it passes through this medium. Now, even after correcting for the dispersion, the quadratic dispersion I just mentioned, some bursts still show this drifting in frequency time, which is linear and not quadratic, unlike dispersion. Sometimes the drifting is seen in subbursts and sometimes within single bursts as well. And lastly, scattering, which scales as the inverse fourth power of frequency. So scattering will be really affects our observations at LOFAR of FRBs. And it has this sort of smearing out effect, which means the burst signal to noise decreases in the burst profile, and that makes detectability harder. So like I said, all these effects scaling so steeply with frequency means it's a double-edged sword. It also allows us to measure all these properties of the bursts with much more accuracy at LOFAR frequencies, and tracking such variations can tell us something about the local environment of the source. I've just listed a bunch of possible progenitor models for specifically repeating FRBs, since that's what I'll be concentrating on today. You have everything from binary models to non-binary models with precession and rotational periods being the cause of periodicity in repeating FRBs, etc. I won't be going into too much detail here. Coming to two of the most prolific, well-studied FRBs, FRB 121102, or the first repeating FRB, and FRB 2018-0916B, or the third repeating FRB. I might keep saying R1 and R3 throughout the talk, so I hope they're recognizable because of the slide. Now, the first repeating FRB, so both of these are, of course, repeating, but they also were observed to have a period. The first one had a 160-day period, while R3 had a much lower periodicity with a 16.33-day period. While R1 was localized to a dwarf galaxy with an associated persistent radio source, we saw that there was no associated persistent radio source for R3, and it was localized to a spiral galaxy near a star-forming region in the spiral galaxy. Now, an obvious choice to do follow-up observations with LOFAR when we had no sources detected by LOFAR back then was the third repeating FRB, since it's super active and has a lower periodicity than R1. While R1 hasn't been detected yet at LOFAR, the first detection of R3 was made at LOFAR by Pleunis et al. And here are a few sample bursts from the source. And as you can see in this particular burst, it extends down to the lowest part of the LOFAR band, which is 110 megahertz. And that is exciting because it means it is possibly detectable at even lower frequencies, and it probably means that there is lesser free absorption around the source, which is allowing us to detect it all the way down to 110 megahertz. Now, what Pleunis et al. Also reported was that the activity of the source R3 was frequency dependent, and that activity at low frequencies here at LOFAR with the purple dots was offset by around 2.5 days when compared to the Chime activity window. So just to explain this plot better again, here is frequency and activity phase across the 16-day period. Now, this delay and dependence with frequency wasn't restricted just to the Chime versus LOFAR band, but was also seen at higher frequencies at L band, reported by Hypernarrow et al. Now, what we wanted to do was continue monitoring this source to see if there is some change to the activity window or some change in how it depends, how the activity depends with frequency. Here, I have the burst arrival time versus activity phase for all the bursts detected so far with Chime and LOFAR. The gray region here is the Chime activity window, while the blue region is the LOFAR activity window. All the bursts below this line here were reported in Pleunis et al. And all the bursts after that are the new results. So this whole time period spans about 3.5 years. And this of course enables us to track the stability of this activity window over such a long time period. Also, another thing we noticed was that the burst rate seemed to be varying quite a bit throughout during these 3.5 years. Now, like I said, we can track a lot of these propagation effects very acutely with LOFAR. And so what we wanted to see is if any of these propagation effects were causing variations in these propagation effects were causing the burst rate to go up and down so drastically. Scattering, like I said, has this smearing out effect with frequency. And here I plot the scattering time at 150 megahertz versus time, as well as activity phase. Up here is the burst rate during each of these 16-day periods where the bursts were detected. As you can see, there's no obvious correlation between this scattering variation in a huge range. It varies between 30 milliseconds to 150 milliseconds, but it wasn't correlated. It's not obvious to us that it's correlated with the variation in burst rate. However, with the scattering with activity phase shows an interesting trend where the scattering time scale seems to be increasing with activity phase. But I think we need more bursts and statistics to ascertain what exactly is happening here. Now, we have also been monitoring the source with the LOFAR telescope between 40 and 80 megahertz and have detected no bursts so far in the past year. While the LOFAR burst activity rate needn't be correlated with the scattering timescale, we can still be limited by scattering at even lower frequencies at the LOFAR telescope with expected scattering timescales of a second or so, which is 20 times more than what we measure at LOFAR. So the second property I'm going to talk about is how the drift rate varies with frequency. Now, this is an example of a burst with two components, and so the drifting is more obvious. Here is the 2D autocorrelation function of the burst through which I make a fit to measure the drift rate. And this is a plot of the drift rates of all the, I think, 26 LOFAR bursts we have had so far. And here you can see that the drift rate versus frequency has this negative slope where it decreases as the frequency increases. And if you put it black, sort of insert this back into this thought from Pastor Mazzola et al., we see that the rate measured here corresponds really well to the rate extending to much higher frequencies till L band. Now, coming to the polarization properties of the burst, we saw Pleunis et al. Reports polarization fractions between 30 to 70% for the LOFAR bursts they reported. I take one of those bursts here. This, for example, I think had 70% polarization over the entire band, and chop it up into 4 different bands in frequency and measure the polarization fraction for each of these bands. And that's what I plot down here for the 4 regions. The red profile is the linear polarization profile. And what we saw was that the linear polarization was decreasing in the same burst across the burst band as you move towards lower frequencies. It is almost linear. I don't have error bars for this yet, so don't take the points in face value, but yeah, there is certainly a trend. Like I said, rotation measure can also be tracked at great precision using LOFAR up to 0.1 radians per meter square precision. I add a few new points to the plot reported by Pleunis et al., where you see rotation measure variations in phase and time of a few radians per meter square, which is much lower than what is typically seen towards pulsars, but which is higher than what is typically seen towards pulsars, but much lower than what R1 exhibits, the first repeater, which shows RM variations of thousands of radians per meter square, amounting to tens of percentage of the total RM for that source. So to put all these properties in context and compare it between R1 and R3, R1 has not been detected at frequencies lower than 600 megahertz yet, while R3 has been. RM variations in R1 are huge, with the absolute RM also being around 100,000, while RM variations in R3 are much lower, with an RM also the absolute value being much lower. R1 has also shown depolarization, but that occurs at much higher frequencies, at about 2 to 3 gigahertz, while it seems like R3 is exhibiting depolarization only at low-far frequencies. So all these 3 properties that I just listed point towards R1 being in a more extreme environment, causing all these huge variations with a higher magnetic field, with depolarization occurring much earlier at much higher frequencies. But there are also similarities, of course, between the two, which is that they exhibit this periodicity. Both these sources have shown this downward drifting subbursts. But while R3 has shown this frequency-dependent activity, there has been no obvious frequency-dependent activity detected for R1 yet. So while it's really hard to tie back all these phenomenological comparisons with a single model, I think there's definitely a lot to be learned about the source using these comparisons. So that was R3. Now coming to other sources that we have been following up with LOFAR all these days.
Just a 2-minute warning, Akshatha.
Thank you.
Just a 2 minutes.
Here I mark all the sources we have been monitoring with LOFAR, which have been follow-up of repeating sources detected by the Chime FRB telescope. And this resulted in a second detected FRB source with LOFAR. We only detected one burst from this source, so FRB 2019-0212b. And here the burst is seen in the full bandwidth. As you can see, it occupies only about 25% of the full bandwidth, which is consistent with what repeaters normally exhibit. And this is chopped to the burst bandwidth. This plot shows the burst chopped to its own bandwidth. Okay, so in summary, continued LOFAR monitoring of R3 points to the activity window being extremely stable over 3.5 years of LOFAR monitoring. But we do see changes in burst rate, scattering variations, RM variations over this whole period. We also see that depolarization occurs in the LOFAR band for this source, unlike for R1 that occurs at much higher frequencies. And we also measured drifting within the LOFAR band consistent with what is observed to much higher frequencies. And of course, the detection of a second repeat in FRB is hopefully a sign that there are a lot more FRBs that can be detected at LOFAR frequencies.
All right, thank you. Lovely talk. Have we got any questions online? I had a brief one. I was just thinking along these lines. So I assume some of these early days of this, you were doing a lot of co-observing, right? As in LOFAR was shadowing Aperitif or something like at the same time. Are you still doing that in terms of like you're trying to get a detection and you can guarantee the relationship between each pulse at different frequencies? Or is it just now just doing LOFAR observing separately to the other telescopes?
Right now, yeah, it's mostly LOFAR observing separately.
Okay, I was just thinking because like with DM and RM measures, you obviously get constraints on the medium that this is propagating through. And I thought another constraint you could also do is if there's any free absorption occurring as well, but that really needs the broadband spectrum to be able to do something like that. But it'd be interesting to test those different models with you observe contemporaneously with LOFAR and say Aperitif or something, and then put the broadband spectrum together. But I'm sure there's a lot more ins and outs there than I fully understand. Anyone else on the call? Last question before we wrap up the session. No, I think everyone's had a lovely 2-hour session there. Thank you again to all our speakers. That was a lovely session on FRBs and transients. Okay, and now I welcome everyone to join the Gather Town if you want to continue the discussion. Otherwise, take a break, and we'll see you back here at 5 UT for the next session, which will be chaired by Paul Schultz on some FRBs and star planet interactions and stuff like that. I hope everyone has a enjoyable lunch if you're in Europe, enjoyable dinner if you're in Australia, good night if you're in Canada. Otherwise, I'll see you guys all later. Thank you. Bye.